Hey guys, Scientistic Moon here. Today we will going to talk about the theory of relativity. As you know, Albert Einstein published the theory of special relativity in 1905, building on many theoretical results and empirical findings obtained by Albert A. Michelson, Hendrik Lorentz, Henri Poincaré and others. Max Planck, Hermann Minkowski and others did subsequent work. Einstein developed general relativity between 1907 and 1915, with contributions by many others after 1915. The final form of general relativity was published in 1916. The term theory of relativity was based on the expression relative theory, German Relativtheorie, used in 1906 by Planck, who emphasized how the theory uses the principle of relativity. In the discussion section of the same paper, Alfred Bucherer used for the first time the expression theory of relativity, German Relativitätstheorie. By the 1920s, the physics community understood and accepted special relativity. It rapidly became a significant and necessary tool for theorists and experimentalists in the new fields of atomic physics, nuclear physics, and quantum mechanics. The theory of relativity usually encompasses two interrelated physics theories by Albert Einstein, special relativity and general relativity, proposed and published in 1905 and 1915, respectively. Special relativity applies to all physical phenomena in the absence of gravity. General relativity explains the law of gravitation and its relation to the forces of nature. It applies to the cosmological and astrophysical realm, including astronomy. The theory transformed theoretical physics and astronomy during the 20th century, superseding a 200-year-old theory of mechanics created primarily by Isaac Newton. It introduced concepts including four-dimensional spacetime as a unified entity of space and time, relativity of simultaneity, kinematic and gravitational time dilation, and length contraction. General relativity is a theory of gravitation developed by Einstein in the years 1907 to 1915. The development of general relativity began with the equivalence principle, under which the states of accelerated motion and being at rest in a gravitational field, for example, when standing on the surface of the Earth, are physically identical. The upshot of this is that free fall is inertial motion. An object in free fall is falling because that is how objects move when there is no force being exerted on them, instead of this being due to the force of gravity, as is the case in classical mechanics. This is incompatible with classical mechanics and special relativity because in those theories, inertially moving objects cannot accelerate with respect to each other, but objects in free fall do so. To resolve this difficulty, Einstein first proposed that space-time is curved. Einstein discussed his idea with mathematician Marcel Grossmann, and they concluded that general relativity could be formulated in the context of Riemannian geometry, which had been developed in the 1800s. In 1915, he devised the Einstein field equations, which relate the curvature of space-time with the mass, energy, and any momentum within it. Einstein stated that the theory of relativity belongs to a class of principal theories. As such, it employs an analytic method, which means that the elements of this theory are not based on hypothesis, but on empirical discovery. By observing natural processes, we understand their general characteristics, devise mathematical models to describe what we observed, and by analytical means we deduce the necessary conditions that have to be satisfied. Measurement of separate events must satisfy these conditions and match the theory's conclusions. Tests of special relativity. Relativity is a falsifiable theory. It makes predictions that can be tested by experiment. In the case of special relativity, these include the principle of relativity, the constancy of the speed of light, and time dilation. The predictions of special relativity have been confirmed in numerous tests since Einstein published his paper in 1905. but 3 experiments conducted between 1881 and 1938 were critical to its validation. These are the Michelson-Morley experiment, the Kennedy-Thorndike experiment, and the Ives-Stilwell experiment. Einstein derived the Lorentz transformations from first principles in 1905, but these 3 experiments allow the transformations to be induced from experimental evidence. The Michelson-Morley experiment was designed to detect second-order effects of the ether wind, the motion of the ether relative to the Earth. Michelson designed an instrument called the Michelson interferometer to accomplish this. The apparatus was sufficiently accurate to detect the expected effects, but he obtained a null result when the first experiment was conducted in 1881 and again in 1887. Although the failure to detect an ether wind was a disappointment, the results were accepted by the scientific community. In an attempt to salvage the ether paradigm, Fitzgerald and Lorentz independently created an ad hoc hypothesis in which the length of material bodies changes according to their motion through the ether. This was the origin of Fitzgerald-Lorentz contraction, and their hypothesis had no theoretical basis. The interpretation of the null result of the Michelson-Morley experiment is that the round-trip travel time for light is isotropic, independent of direction, but the result alone is not enough to discount the theory of the ether or validate the predictions of special relativity. General relativity has also been confirmed many times, the classic experiments being the perihelion precession of Mercury's orbit, the deflection of light by the Sun, and the gravitational redshift of light. Other tests confirmed the equivalence principle and frame dragging. Far from being simply of theoretical interest, relativistic effects are important practical engineering concerns. Satellite-based measurement needs to take into account relativistic effects, as each satellite is in motion relative to an Earth-bound user, and is thus in a different frame of reference under the theory of relativity. Global positioning systems such as GPS, GLONASS, and Galileo must account for all of the relativistic effects in order to work with precision, such as the consequences of the Earth's gravitational field. This is also the case in the high-precision measurement of time. Instruments ranging from electron microscopes to particle accelerators would not work if relativistic considerations were omitted. Thank you for watching the video till here. Have a nice day. Subscribe.